Hello students, welcome to Horario class 10 physics classroom. In the last class, we discussed our first chapter and the energy conversion. In the energy conversion module, we discussed how the electrical energy can generate different type of energy forms. From that, we understand that the electrical energy can be used to generate different types of energy. For example, light energy, sound energy, heat energy, also magnetic energy. From the chapter 2, we discussed that when a current carrying conductor is subjected to pass a small amount of current or a small amount of voltage through it, it will generate a magnetic field around it. So from that session, we are very well know that the electrical energy can also generate magnetic effects. For example, we are considering a solenoid. This solenoid is connected to a energy source, a voltage source, which is controlled with a switch. So the coil type structure is known as solenoid, and this is known as battery or cell, and this is known as switch. When the switch is in the on position, we all know that the current will flow through this circuit. And from the second chapter, we are very knowing that when the current flows through this circuit, this solenoid will act like a bar magnet. What is the importance of a magnet? Magnet means it have two poles which is known as north and south. So when the current passes, this solenoid will change to a bar magnet. In the magnet, we know that it have a field of attraction, which means this magnet have a special property. It can attract some material. We all know that the magnet will attract the iron. So it will attract different type of material. And this field is known as magnetic field. Magnetic field. So when the current passes through a solenoid, it changes to a bar magnet and a magnetic field is produced around it. So from this, we can conclude electrical energy can be converted into magnetic properties or magnetic energy or magnetism. Electrical energy can be converted into magnetism. So from this property, we are trying, if the electrical energy can be converted into a magnetism, we can also produce electrical energy from the magnetic property of a material. In the second chapter, we discussed how the loudspeaker works. Also, we discussed about a motor. In these two instruments or the electrical equipments, the electrical energy helps to form the magnetism inside these two equipments. So here we are discussing how can we convert the magnetism of a special equipment or a material can be used for deriving electrical energy. And it's one of the most important chapter we are going to study in our 10th classroom, because it is one of the most lengthy chapter in our textbook. So we are going straightly to the textbook chapter number 3, Electromagnetic Induction. Okay students, when we are discussing the electromagnetic induction, our third chapter, we are starting with a small experiment. In this figure, you know that these three equipments which have been drawn here. The first one is a magnet. The magnet which has a north pole and also a south pole. And this is, you all know this is known as solenoid. And an equipment is placed here and it's write that it's a capital letter G. And it stands for galvanometer. Galvanometer. You all know that what is the importance of galvanometer. Galvanometer is used to find the direction of the current flow in a circuit. So with the help of a galvanometer, we can know that is there a current passing through this circuit. So in this experiment, we are going to pass this magnet into this solenoid. In the first time, this circuit is placed stationary and the magnet is passed into this solenoid. When the magnet enters to the solenoid, we can see there is a small deflection in the galvanometer. In the first instinct, when the magnet is entered to the solenoid, we noted a small change of values in the galvanometer, which means when a magnet with a magnetic field passed to a solenoid, it resulted in the formation of a small amount of electricity. So when the magnet passes through a solenoid, it will lead to the performance, or it will lead to the formation of small amount of current. In the second time, in the first time, we moved the magnet, and electricity formed. In the second instinct, or in the second time, we are placing this magnet inside the solenoid. This magnet is placed inside this solenoid. There is no movement involved. The magnet is placed stationary inside the solenoid. The magnet and the circuit not moving. In this time, there is no change in the value in galvanometer, which means there is no electricity produced. In the later session, in the third time, we moved out the magnet from the solenoid. We placed the magnet in the outside position. When the magnet comes out from this position or from the solenoid, we can denote or note a small change in the galvanometer again. In the last time, the magnet is moved out, and in this same time also the electricity produced. The electricity formation it can be known from the values changing in the galvanometer. So from this experiment, we can say that when the magnet moves through a solenoid, it will result to the formation of electricity. What happens when the magnet is not moving or magnet is kept stationary? In that time, there is no electricity is produced. What is the reason? The main reason is, we already discussed, there is a field which is known as magnetic field. What is meant by magnetic field? Magnetic field is the imaginary lines or imaginary portion around the magnet where the force of a magnet can be experienced. If we have a magnet, we all know that it will attract a piece of iron. But what happens? The iron is placed very in a different or far away from the magnet. It will not attract the iron piece, because each magnet have its own magnetic field. Some magnet will have small magnetic field, and if the magnet is very strong, it have a very big magnetic field. So when this magnetic field is interfered by the solenoid, it resulted to the formation of electricity. So from this, it is very important to know that the magnetic field, the change of magnetic field or the interference in this magnetic field which is caused by the solenoid resulted to the formation of electricity in the galvanometer. So if we also place this magnet inside the solenoid, there is nothing happen to the galvanometer, because the motion of the magnetic field is very important. Okay, in the next condition, we can make the magnet stationary and we can move this circuit. What will be the formation, or what will be the conclusion can be derived from this experiment? It will be same as the first one, because the magnetic field is placed stationary, or the magnet is placed stationary, and the solenoid is moving. When the solenoid is also moving, the interference can be happen and the galvanometer can be shown a small amount of energy or the electrical energy formation. The first thing we want to know that if an interference happens to the magnetic field of a magnet, it can be resulting to the formation of electrical energy. So here the most important thing is a solenoid which is made up of a conductor in a coiled manner is placed and a magnet is passed through this solenoid, and the magnet is continuously passing through the solenoid without stopping. We can harvest unlimited amount of current or unlimited amount of electrical energy from the galvanometer. So the motion is playing very important role. So from here we can know that the main conclusion is the magnetic field and the interference of magnetic field with a conductor will result to the formation of electrical energy. And what are the factors affecting this electrical energy production? The factors affecting electrical energy. From this experiment, we can conclude the first factor which is influencing the electrical energy production is motion. Motion. If we are moving this magnet in very fast manner, we can produce large amount of energy. If we are moving this magnet in a slow manner, it will result to the formation of amount of energy in small manner. So the motion also can be termed the speed of movement. Speed of movement of magnet or the circuit. When the fast motion will result to the production of large amount of electrical energy, and the slow motion or the slow movement will result to the small amount of electricity production. What will be the second factor that can be affected for the electrical energy production? What if I increase the number of coils or increase the turns in this solenoid? When the number of coils increased in the circuit, what happens? The interference with the magnetic field will increase. When the number of turns increases, the interference with the magnet also increases. So I am increasing the number of turns inside this solenoid will also eventually result. What will be the result? The energy production in this circuit will be very high. So the second factor is number of turns in a solenoid. And what will be the third factor? From this you can all say that when the power or a magnet with high magnetic field, it can result to the formation of large amount of current. When a magnet with high magnetic field, it will result to the interference, a high interference with the solenoid, which will help for the production of large amount of electrical current. What happens? A magnet placed with a small magnetic field, the production of energy will be very less. So the third one is strength of magnet. So this is the three factors which is influencing the production of electrical energy which is produced inside this circuit. Here you all want to notice one thing, there is no battery is involved, there is no switch is involved. What is the reason for the production of electrical energy? It is the mere chances of, or it is only because due to the movement of this magnet or due to the interference of magnetic field. So here we see that this magnetism or the magnetic energy or the magnetic property influenced for the production of electrical energy. So here we can say that the electricity which is flowing through the circuit, the electricity which is flowing through the circuit is formed due to the induction of this magnet. This magnet is induced. The magnet is induced the current inside this circuit. So we can say that the current produced in this circuit as induced current. Induced current. The current which is formed in a circuit due to the induction of anything For example, induction of a magnet, we can say that as induced current. You all know that according to Ohm's law, if there is a current, there will be voltage. So, the voltage induced by the phenomenon or due to the magnet, it is known as induced voltage. Induced voltage. Sometimes we all call this as EMF. Sometimes we will call it as EMF. It's the short form which stands for electromotive force, which is very important. So, from this experiment, we can conclude that the motion of a magnetic field inside a solenoid will lead to the formation of induced current and the induced voltage. The induced voltage is also known as EMF, which is known as electromotive force. So, from this, we can say that when a coil is induced with some of the magnetic flux, or the magnetic flux linked with a coil changed, there will be a production of induced voltage, or there will be a formation of EMF. So, this phenomenon or this formation of EMF due to the change of the magnetic flux linked with this solenoid or the conductor is known as electromagnetic induction. This process is known as electromagnetic induction. The principle of this thing or this whole phenomenon is very clear from the name itself, electromagnetic induction. The induction of electricity with the help of a magnet, it's known as electromagnetic induction. As you all know, this is first proposed, or this idea was first proposed by the famous scientist who is Michael Faraday. Michael Faraday experimented with the magnet and a current carrying conductor, and he noted that when a current carrying conductor is introduced to a magnetic field, there is a motion is involved. You all studied in the second chapter. Then he wondered how can we produce or how can we use this motion into production of electrical energy. Then he experimented more and more. At last, with the help of this electromagnetic induction, he developed the new theory, so that he is known as the father of electricity. Okay students, then we are moving on to the next session. In the second chapter, we know that when a current carrying conductor is placed into a magnetic field, it will result to the motion, or we can harvest mechanical energy from that instrument. Like that, we discussed the motor principle, and we also studied how the motor works. Here also, the same principle is taking place, but in a vice versa. What happens here? Here, the magnet is moving, and the motion of this magnet and the magnetic flux linked with this solenoid lead to the formation of electrical energy. So, here also, we can find the direction of the induced current formed inside the circuit. For that, a scientist named Fleming developed a rule which is known as Fleming's right hand rule. So, you all know that how the right hand rule works. You can extend your hand and the three fingers, the thumb, the forefinger and the middle finger. The thumb denotes the motion of conductor, and the forefinger shows the direction of magnetic field. And what the middle finger indicates? The middle finger indicates the direction in which current flows. So, with the help of these three fingers and the fixed position of each parameter, we can say in which direction the current is flowing. So, I am keeping, just imagine there is a two magnet is placed here, one magnet north pole and the one other magnet with south pole. What happens in the opposite poles in coming near? The two poles will attract each other, which means there will be a magnetic field forming in between them. So, when a magnet or a conductor is placed between this and the motion is taking place, the conductor is moving from up to down. The conductor is moving up to down and the direction of magnetic field in this direction. So what will be the direction of current? The current will be moving to this formation from to the left of my arm. Okay. From this or with the help of Fleming's right hand rule, we can decide in which direction the induced current is flowing. Okay, and this is one of the most important question we can expect for the SSLC examination. So people, in the textbook page number 19, you can see a violet colored box which is discussing the Fleming's right hand rule. Please put an important sign or star sign. You can read it every time when you are going through the textbook. Okay, here we discussed how the electricity is producing inside a current carrying conductor. Here, the current can be produced in two ways, and commonly these two type of currents are known as AC and DC. You all know that, you all heard about this AC and DC. The AC stands for alternating current, and then the DC stands for direct current. So the energy production or the electrical energy production is taking place, and the two type of current can be produced with the help of electromagnetic induction, and the one is AC and the other one is DC. The expansion of AC stands for alternating current and DC is direct current. The first one and the second one. For example, what's mean by AC? The AC current means that the current which is constantly changing its direction is known as alternating current. It is alternating the direction of the flow of this current. You all know that if we draw a graph with x and y axis, this portion will be the positive and this portion will be negative. And equivalent to the y axis, the upward direction shows the positive sign and the downward direction shows the negative sign. So here in this y direction, if it goes upwards it will be positive and if it goes downwards it will be negative. So here we can say that the alternating current moving through positive and the negative region. So it is alternatingly changes its direction. So the name alternating current is K. Okay, then what will be the reason for the name direct current? From the name itself, we can say that the current which is not changing its direction, it's known as direct current. For more easy understanding, we can draw the current which is not changing its direction. Here what's happening? The current is only moving through the positive side. There is no current in the negative side. So here the current is going only through one direction and it is known as direct current. And when the current passing through the alternating charges, it can be termed as alternating current. And with the help of electromagnetic induction, we are producing two type of current and they are known as alternating current and direct current. So as an introduction of our third chapter, we discuss what is meant by electromagnetic induction. For that, with an experiment, we explain when a magnetic field or a magnetic flux linked with a solenoid changes, it will lead to the formation of induced current. Like that, if the induced voltage is produced, we will call it as EMF, electromotive force. So the flux linking with a solenoid resultant to the change or the production of electrical energy or electrical voltage, it can be termed as electromagnetic induction. With the help of electromagnetic induction, we are producing two type of currents, and that is, or they are, alternating current which is termed as AC and direct current which is termed as DC currents. Okay. For also we discussed the Fleming's right hand rules, which decides or which explains the direction of current which is formed in a electromagnetic induction circuit. So this is the introduction for our third chapter. So we can go into the detail of this chapter in our next session. So if students have any type of doubts or any kind of questions, please let me know. You can comment it in the comment section. Okay, for more videos of this link with the physics 10th chapter, you can subscribe to the Horario channel. There will be more videos coming, and thank you.